Okay, welcome to Math 315 analysis, and this is the second recording of chapter 6. Just to summarise the bare bones of what we did in the last recording, we've talked about a sequence AN being a Cauchy sequence. The definition was if we're given epsilon bigger than naught, then there exists some number capital N, which will depend on epsilon, so that if we take terms in the sequence beyond that point, then the difference between these two terms is less than epsilon. That is, eventually all the terms get closer and closer together. We then looked at a particular example of a sequence where the difference between successive terms was less or equal to 1 over 2 to the n, and we saw that that was a Cauchy sequence. And we used that then to examine the sequence with this property. If you've got a sequence where the difference between two terms is less or equal to a half times the difference between the terms just less than that, then that sequence also was Cauchy. And of course the key theorem here was that all Cauchy sequences converge. Now this line here in particular is an interesting one, and that's the one we're going to concentrate on and try and generalize and be more specific about. And in fact, we're going to call a sequence that obeys some rule like this one, we're going to call that a contractive sequence, and we'll see then that contractive sequences converge. And they're the sorts of problems that you'll be asked to work through, and I'll do an example of that. So here's our definition. So we're going to introduce this new word, a contractive sequence, one which is getting smaller, it's contracting. So a sequence A is called a contractive sequence if the difference between these two successive terms, one after the other, is less or equal to some number k times the difference between the terms just back from that one. So you might like to just think about a little picture here. So we've got AN plus 2 and then AN plus 1, and we're measuring the distance between these two has to be less or equal to some number, that k, so that this distance is less than k times this distance, where this k is strictly between 0 and 1. So the difference between here is less or equal to k times the distance in here, where this k has to be strictly between 0 and 1. Now, our main theorem here, theorem 6.2, says every contractive sequence of real numbers is a Cauchy sequence, and hence it converges. Now, I won't go through the proof of that. It's very similar to what we did in the previous recording. It's very similar to the previous example. We just replace the half by some number k between 0 and 1, and then it follows exactly through the same argument. Now, the next example are the sorts of ones that you might be asked to do. This is fairly standard examples on these contractive sequences, but we take you through line by line to tell you what to do at each stage, so it's not quite as frightening perhaps as it might first appear. Now in this sequence, every term it's 1/5 the term before it plus 4/5 the term before that, and I'm going to start off with x1 is 0, x2 is 1. And we're then asked to find the next two terms in the sequence. That's easy, we just use the recurrence. We're then going to show that the difference between these two terms is 4/5 the difference between the two terms further down, and so that will then mean it's a contractive sequence, therefore converges. Then we're going to show that if you take any term plus 4/5 the term before it, then that equals the term before it plus 4/5 of the term before that. And we're going to use that then to find the limit of the sequence. So here are all the calculations worked through in detail. So here's our sequence. So xn plus 2, it's 1/5 the term before plus 4/5 the term before that, and there are our two initial conditions. So x3, I'm just putting n equals to 1 into here. So it's going to be 1/5 times the previous term plus 4/5 times the term before that, and that's just 1/5. So notice the sequence is not monotone. It's going 0 up to 1 and then back to 1/5. The next term, well, again, you go back to the recurrence. It's 1/5 times the term before that one plus 4/5 times the term before that one. So that's 1 on 25 plus 4 on 25, and if you multiply it by 5, you get 21 on 25. So again, notice it's going from 0 up to 1, back down to 1/5, up to this one. So the terms are not monotonic. So we can't use them. It's not going to be amenable to the monotone convergence theorem here. Now, the next part said we had to show that this is true, that the difference between any two terms is 4/5 times the difference of terms just back from there. So we simply plug it into the recurrence. So that minus that's the left-hand side. We can replace this one. It tells me this one is 4/5 times the term before that plus 1/5 times the term before that plus 4/5 times the term before that, and then I've got minus xn plus 1, so that's 4/5 xn, and then 1/5 minus 1 is minus 4/5, and I can take the 4/5 out. I can factor the 4/5 out. Because it's absolute value, I can just multiply this inside by minus 1 and flip the terms around, because it's absolute value, and I get xn plus 1 minus xn. And that's what we were asked to show. The difference between two terms is 4/5 times the difference between the two terms further back. Now, the third part said to explain why it's a contractive sequence. All we have to do here is simply to note that 4/5, that's the coefficient here, is less than 1. And so because of that, the sequence is contractive, and hence it is a Cauchy sequence, and hence it converges to some limit L. That's all we have to do there, is just simply to observe that it is a contractive sequence because 4/5 is less than 1. And then our theorem says, therefore, it's a Cauchy sequence and it has some limit L. Now, by the way, you can check it, but there's no point taking limits back in the original recurrence, because once again it just gives you L equals L, which is not very useful. The next part, we are told to consider each term plus 4/5 times the term before that one. I want to look at each term plus 4/5 times the term before that one. And we're asked to show that's equal to the term before plus 4/5 times the term just before that one. So once again, all we need to do is we copy down the left-hand side, and I'm just going to use the recurrence again to replace xn plus 2 is 1/5 times xn plus 1 plus 4/5 times xn, and then I copy that down. And now when I add these two terms together, I get 1/5 plus 4/5 is 1, and I've got 4/5 xn, and that's all we had to do. So we can continue now the pattern. We simply pull every term back, every bit back by 1. So this is that goes back to that. So the next one's going to be back to xn, and so on. And we can continue all the way down. So continuing thus is what we say in mathematics. We can continue this all the way down to the beginning, which is x2 plus 4/5 x1. And x2 had the value 1, and x1 had the value 0, so that turned out to be 1. We can now take limits through this equation, and we know this one's going to some limit L. This is going to L as well, so that's L plus 4/5 L equals the 1 from there. Well, 1 plus 4/5 is 9/5, L is 1, and so L is equal to 5/9. And so this sequence is going towards 5/9, which is 0.5555, so on. And that's the end of that particular example. So that's not too hard. I hope you see. You just follow through what it tells you to do, and you can prove that these sequences converge. Now I wanted to do another example of one of these. If I can find the right page. Well, the next example here the next example here is to again, a little bit less detail here. This time we're not taken through it quite so much, but it says consider the sequence defined by A1 is 1 and an plus 1 is 1 plus a half n. So this time every term in the sequence is 1 plus a half the term before it. And we start off with 1. So you can see the next term is going to be, well, we can work it out here. It says show it's a contractive sequence, hence converges, and find its limit. And so here is the question again. First term is 1. Every term is 1 plus a half the term before it. So just to see what the first few terms look like, if we put 1 in here, we get 1 plus a half is 3 halves. And then we get 1 plus a half of this, that's 1 plus 3/4 is 7/4. And we can continue on. So this is 1, this is 1.5, this is 1.75, so it looks in fact like this one may even be increasing, but we're going to show this is contractive. So to show it's contractive, we need to show the difference between any two terms. We've got to connect this back with an plus 1 and an. So I'm going to replace this one here with 1 plus a half an, and then I've got minus an plus 1. Now the point here is that I'm not going to combine these, I'm going to use the recurrence on this one. That makes it just slightly more tricky, so I copy that one down and I apply the recurrence back up here to this term, so I get 1 plus a half n. Now the 1's cancel out and I just get 1/2 an plus 1 minus a half an, and so I can factor the half out of that. So just note what I did there. I used the recurrence on this one and I used the recurrence on this one, and that got me back to when we all simplified, this simplifies back to something involving an plus 1 and an. Now, so this half out the front here is less than 1, so the sequence is a contractive sequence because the coefficient here is less than 1. And hence this converges to some limit L. Now this time we can just take a limit straight through the sequence, back up the original sequence. We can just take a limit through here. We get L is 1 plus a half L. So that gives me a half L is 1, and then L in this case, in fact, it's getting closer and closer to 2. And that's the limit there. So that is another example of one of these contractive sequences, and you'll see that we'll be looking at several more of these in the tutorial problems. We're going to move on now back to functions again, and we're going to have a look at this idea of differentiability. So in calculus courses, you learn that the derivative of a function is the measure of the rate of change of the function, or probably also you've seen it's the idea of the gradient of the tangent of the function at a point. So we're going to be considering here exactly what we mean by differentiability. For example, let me just show you a rather horrific function here. Here is a rather ghastly looking function. This function in fact is defined by an infinite series. If you've got a graphing calculator, you might like to try one of the, if it'll do something like this, you might like to try it. But what I did was I replaced infinity here with, I think, 100, because it couldn't cope with, you can't put infinity in here. So I put 100 and just took the sum of the first 100 terms of this and then plotted it. So notice you've got two variables here. You've got an n that you're summing over, and you've got an x in here. And the picture that the computer produced, in fact it actually continues up here, but I only printed out a bit of it. So, but you can see it's going crazy at every point. It's got all these sharp corners. And in fact these sharp corners are happening at every point. The computer can't draw this, but they're happening at every point. This function, in fact, as I mentioned, it continues up here beyond what the screen could do, but this function happens to be, in fact, continuous. But you can't get the derivative anywhere. It's got no derivative at any point. No derivative at any point. And the reason being is that if you try and differentiate this thing, what you get is an infinite series that diverges. So this infinite series converges, that makes it continuous. But if you take the derivative, then the derivative of this doesn't exist anywhere because the infinite series you get diverges. So it's an amazing example of a function that is continuous everywhere but differentiable nowhere. So you see, we have to really worry about what we mean by differentiability to be able to make sure we can classify objects like this one here, which look horrendous, but it is continuous everywhere. You can draw it without taking your pen off, but it's differentiable nowhere. And in the next recording, we'll make a start looking at the notion of differentiability and look at the definition of it.